Okay, so here is the last big thing we will talk about. And this is the different types of nuclear decay that you can go through. So, the most famous one, and this is what Rutherford uses, what's known as alpha decay. And there's different elements that can go through this. So the cool part about alpha decay is to figure it out, all you have to be able to do is add, okay? Because mass has to be conserved. So typically you talk about two types of things when you talk about decay. You talk about the parent and you talk about the daughter. So if uranium-238 undergoes alpha decay, so what's going to be different about this is that you change both mass number and you change the atomic number. So this is why if you can add, you can do alpha decay. Because if you've got 92 over here, when you get done on this side, guess what? Everything just has to add up to 92. So if it's an alpha particle and it's helium, you're losing the 2 protons. Oh, okay, 2 plus 90, boom, I get 92. Cool. The mass number still has to add up to 238. So if I take 4 plus 234, I get 238. So alpha decay, mathematically, is the simplest. Make these add up to 92 or whatever you started with. Make the mass numbers add up. One shrinks by 4, the other one shrinks by 2. That's it. Just make them add up. That's the simplest one. Now, where it gets a little sketchier is what we call beta decay. Now, here's the, and that's carbon 6, not carbon 12. Hold on. That's not going to make any sense at all. That should be carbon 6. So, when you have beta plus and you have beta minus decay. And it works the opposite of what you would think in terms of the words that we use to describe it. So on beta minus decay, then beta minus is the one that happens most often. What you do is you keep the same number of particles in the nucleus, okay? So on both of these, you'll see that the mass number stays the same, okay? So that makes it simple. But this is where it becomes a little bit counterintuitive. So we're going to keep the same number of particles, a total number of 14, but we're going to go from having 6 protons into having 7 protons. So what happened is that one of the neutrons changes into a proton. Okay? So you're increasing the atomic number by 1. And as soon as you change the atomic number, what happens? The element changes. So now, to make the charge balance out, because you've gained a positive charge within the nucleus, so charge has to be conserved, so a byproduct out of that is you kick out an electron. So you're gaining a positive charge, but to balance the universe, you create an electron so that everything still adds up to the same overall charge in the universe, okay? So the reason that they knew this was happening is that they were looking at samples of carbon-14, and what they were finding, even though it was a completely isolated system, they would see an increase in the number of nitrogen atoms in the sample, which didn't make any sense. It was like, this is completely isolated. How can we be getting nitrogen? And this is the only way that it made any sense. So most often it's beta minus. Now, you can have beta plus, but this is why I said it's the opposite of what you think. So in beta minus, you add a proton. So in beta minus, you add, okay? Now, in beta plus, and this is why this is more rare, in beta plus, you subtract. So what happens there, again, you keep the same mass number, which in this case is 23 for magnesium. But you're going to go from 12 down to 11. So the same thing was happening. They were seeing pure samples of magnesium, but they were seeing elements of sodium start to show up in it. And it's like, this is weird. How do you explain the sodium showing up? But what's weirder is that you kick out a positron. So a positron is the exact same as an electron, but it has a positive charge. So everything about it is the same, but it has a positive charge. This is what's called antimatter. Now that's cool, but here's the problem. If an electron ever runs into a positron, anybody know what happens? They annihilate each other. They turn back into pure energy. Okay? So this is why you can't say, oh, well, I'm going to build an antimatter box. Okay? Well, you can't, because if you have antimatter, then it's just going to run into normal matter. Okay, I know South people have to go. So this is out of chapter 30. This is obviously not due. These are problems that you need to be able to work. I've got them all worked out for you. These are just not the answers. I've got everything worked out. So we'll talk about this tomorrow. We'll review the test on Monday. Okay, let's say on a scale of 1 to 10, let's say the magnetism is more than 8. This is probably a 6. Okay?
I saw Charles' eyes when he said magnetism was an 8. Charles went,
Yeah.
Magnetism is 10 is 8.